Hey, what's up everybody? Mr. Murray here, and we are back on Mr. Murray's Mathland doing some more derivatives with logs, but this time logs with bases other than e, so not the natural log, which usually to this point in the course is the only kind of log you've dealt with. So bad news if you don't like ln's though, because it's all based on ln. So keep in mind that rule here, because it really does come into play, that the derivative of ln of x is 1 over x, or ln of u is 1 over u times u prime, right? So keep that in mind, because it's going to be a very similar rule for other logs. And there's so many rules you have to memorize, and I teach this from an AP Calc standpoint, where you're going to have to take the AP exam and you don't get a formula sheet. So if you can't remember these rules for these other logs, logs with other bases, they don't pop up that frequently, first of all, but you can always, if you're good with your pre-calc, you can always sort of derive the rule on the spot. And this is not a terrible one to do. So it would be using the change of base formula. Now, as you learn it in Algebra 2 or pre-calc, that you can convert any log of any base to probably base 10 is what you're taught, or ln, because those are the buttons the most scientific calculators have. So, a lot of times in Algebra 2, you might deal with base 10 primarily and say, okay, well, that's log of x over log of 15, which is true, of course. But hopefully you also remember that you can convert it to any log of any base. And so we want to use ln because that's the one log we have a derivative rule for at this point. And that would be ln of x over ln of 15. So that's all I did here, was I took this and changed it into another expression with ln's, and I'm going to do that derivative now. And if you're thinking that that's going to be the quotient rule, hopefully you really recognize that this right here, 1 over ln of 15, that's just a constant. There's no variable in there. And so it's being multiplied by ln of x. And so the derivative here we're going to come up with is 1 over ln of 15 times 1 over x, the derivative of ln of x. So you get that very similar rule here that, if you like, and I'll go with, again, using the u rule here, that if it's log base a of u, so it's some other base other than e, then what you're always really going to do, if you want to just take a look at what I just did here, is that you get 1 over ln of whatever that base is, right? We used base 15 in the last problem, and you just get 1 over ln of that base. So like I said, it's still ln's, and then it's basically the ln rule for this quantity, 1 over u, and if chain rule is necessary, times u prime. So a lot of people will just kind of go right to this, and they'll have ln of a times u right in the denominator. So very similar to your ln rule. Like we said, u prime over u, but it's got this additional little factor of ln of a in the denominator. Okay, so if you feel comfortable with that, you can really just fly through these pretty fast if you're good with your ln rules. And so you take a look at this problem, find the derivative of log of x cubed minus 8x. And if you don't see a base written, remember in this context that means base 10. That's an implied base of 10. And that, again, it may be base 10, but it's not base e, so it has to be converted to natural log. Or if you're comfortable with the rule, just make your fraction and say, hey, it's going to be ln of that base in the denominator times, and then use your typical ln rule for this quantity, right? So times, oops, converted back to my pen there, 1 over x cubed minus 8x, and multiplied by that quantity's derivative on top, which would be 3x squared minus 8. And there you go. And sometimes these, these ln of these constants, they just kind of look awkward hanging around. Some people will put them after, some people will put them before the quantity. You know, there's almost no good way to make some of these things look pretty. So that's it. Good. Here's another one, just so you get the hang of it. Threw a little trig function in there. This one is base 4. So its derivative will be 1 over, that's base 4, so we'll just throw an ln of 4 in the basement here, if you like to think of it that way. And the derivative for ln of cosecant of x would be 1 over cosecant of x, and then multiplied by cosecant of x's derivative. So derivative of cosecant of x is negative cosecant x cotangent x. Kind of nice that cosecant of x actually will cancel. So you get a slightly simpler looking fraction of negative cotan x over ln of 4. There we go. And let's just take a look at, say, one more here. Just mixing it in, doing a variety of things. So this time you have a log, but on the inside of a trig function. So just keep it in practice with your chain rule, that to do this derivative, tangent is the outer function, the outermost function, so that must be, you know, kind of dealt with first. The derivative of tangent of something is secant squared of that something. So secant squared of this log base 7 of x, you know, just be slow and methodical. Then multiplied by the derivative of that inner expression. So here's your chance to use your new log rule we just learned. So multiplied by the derivative of a log, make your fraction. It's not ln, it's not base e, so you have to put an ln of 7 in the basement there. And it is just x, so it's just going to be 1 over x. And that's that. Sometimes people will put a parentheses around like the ln of 7 to show that that's definitely not 7x that's on the inside of the natural log there. You know, it doesn't hurt to have some extra stuff, and this would probably be written as a nice fraction like this, with ln of 7 times x, or people put the x in front of the ln of 7 if you like. But there you go. Anybody want to do the second derivative on that now? Probably not, but you could if you had to. And that is it. So if you have any other questions, hopefully this was showed you at least a variety of problems to answer. But if you have any questions, let me know, and hang in there and keep working hard, kids.